After showing his sources to either not exist or not saying what he wanted them to say in this video, we will focus on calculating that we can actually see the stars and the planets exactly the way that we do, and we will use his own numbers to do so, so stay tuned. Hello everyone, welcome to part 2 of the video discussing Kryptonite Physics assertions about impossible things. Now we will have a look at planets and stars, after which I will show my calculations and we can together find out that they are, unsurprisingly, not a problem. By the way, you might have noticed that my audio has gotten better. This is because I realized that I had one setting about the recording quality turned very much down. I do apologize for the last 50 videos, I guess. So yeah, we now know.
The inverse square law of light, along with the limitations of the human eye, control all we can see.
Sure, I guess.
As you look at the night sky, on a clear night, you see an abundance of lights, with different colors and brightness. Light travels from the sun to each planet.
That is
Some
correct.
of that light is reflected. It then travels over vast distances to Earth, and your eye.
We don't need to go through the whole thing. Essentially, the assertion here is he calculates about the moon, and he figures out that at one moon distance, the light that is reflected to the moon turns out to be around 0.5 lux, so that we can see the moon. And he now makes some calculations for every planet of how much light they would reflect, and then how much this would be at a given distance, and then he comes to the conclusion that this is not enough light to see. Now, would he have stuck, because this is actually a contradiction to something he mentioned in video number 3. You see, one of the sources in video number 3 clearly states, I hope future Olaf has the mind to insert this here, states that 5 to 7 photons are about 10 to the minus 4 lux. We here have 10 to the minus 6 lux. And of course, if 5 to 7 photons are 10 to the minus 5 lux, 10 to the minus 6 lux would be 0 point some amount of photons. So this is not a self understanding and not self-supporting model that he has here. Apart from that, we have shown in the past, in the part 1 of this video series, that the limit to human vision is in fact not what Kryptonite Physics claims. So the point about the lux is completely superfluous, and I do challenge you, Chris, here within this video later, I'm doing it now, but I will do it later as well, to calculate it decidedly with photons.
This is the level of visible light arriving on Earth and your eyes. With the naked eye, or even an optical telescope, your eyes would not have enough light to see anything.
I like how he says with an optical telescope as opposed to a non-optical telescope. I suppose he means a telescope that observes in the optical range of light. But I assure you, particularly with the big ones, maybe not with amateur telescopes, although those are extremely respectable oftentimes and can produce extremely good images, we will be able to see that. At the latest, if we use exposure, which he shows in part, I believe it is part 6 that he doesn't understand how exposure works, which we will talk about in the next video, just so we are on the same page.
Yet we do. The planet Mars. Mars at its closest is 55,650,000 kilometers away from Earth.
Note that his calculations are, as far as I understand it, with the closest. My calculations are with the distance always from Sun to the planet. So I always say that the Sun is as far away from the planet as Earth is, which is technically a special geometrical position, but it will give the correct order of magnitude. But we'll talk about this later.
At its furthest, it's 300 million kilometers. With the naked eye, we can see its light and color.
That is
Mars
correct.
at its closest is over 139 times further than the Moon. At its furthest, 750 times.
And again here with the calculations showing that this would not be enough lux, I would just like to point out here he uses lux as Lx, which is the physical short form of lux, and here he writes lux out. I don't know why, this just seems confusing.
At Mars's stated distances, it would not be visible, let alone visible in color.
Again, we disagree, as we have shown in the last part about human vision.
It reflects less light than the moon and is over 139 times further away.
That is correct.
To put this in context, a framed image of Mars with just the moonlight illuminating it. You have 1,000 times more light hitting your eye from this image, yet see no color.
The thing about seeing color is that it has something to do with contrast as well. It also has things. Now, obviously, if I'm at home and my room is dark and I close the blinds and I don't see anything within my room, things do indeed seem gray. But for all practical purposes, even though the planets don't emit light themselves, they do appear as if they would be self-illuminating. And the small point from which all of that light reaches the eyes, because all of Mars's light reaches us through essentially one point at the sky. So it's not spread out. It's coming from one point, thus allowing us to see color. Because seeing color doesn't only have something to do with light intensity. It has loads to do with contrast and all those other kind of things. You can't make a blanket statement about that like that.
None of the planets would be visible. Mars, Jupiter, Saturn, Uranus, and Neptune would not send your eyes enough light to see them in color or see them at all. They all reflect less light than the moon. The only
they reflect more light than the moon, but less light of that reaches us. I guess it depends on how you put it. Because less light reaches them, you could say that they reflect less light, but in terms of how much light they could reflect, because they're way bigger and have a higher albedo, generally speaking, they could reflect more. Semantics, not important.
Explanation there can be, with the color and lights we see, is that the planets are a lot closer than we're told.
Or your assertion is wrong, which we know that it is. Now, I would like to go immediately for the second video, as you can notice, and then I would like to present my own calculations where I show that indeed things are precisely the way they should be.
We are told the Sun is about 150 million kilometers away from Earth, or 1 astronomical unit, AU for short. At my latitude, the reading for direct sunlight is 100,000 lux. How?
At Earth, it depends. The latitude, of course, plays into that. The highest thing you can get, I believe, at the distance of Earth would be about 110,000 lux, I believe it was. Which is interesting because in the previous video he claimed the moon would be illuminated by 130,000 lux, which seems somewhat contradictory, as the moon is basically the same distance from the sun as Earth is, but whatever. Maybe these are atmospheric effects taken into account.
Would it need to be to not be visible? Be below 0.0001 lux of its light, hitting my eye? The answer is 31,623 times further. 0.5 light years. What if the sun was 10, 100, or 1,000 times brighter? At 10 times the brightness, 1 million lux on Earth, it would not be visible at 100,000 AU, 1.58 light years. 100 times the brightness, 10 million lux on Earth, not seen at 3.
I'm not addressing any of this specifically, because this is just again building off of the assertion that you can only see around 0.00001. I'm not sure about the last 0 lux. Which we have already talked about in part 1, is just not the case.
116.
Oh, that's interesting. That has never happened, I do apologize. Okay, there seems to have been a little problem with my internet. It is back now, we can continue.
116,228 AU, or 5 light years. and at 1,000 times the brightness, 100 million lux on Earth, invisible at 1 million astronomical units.
Which again, I will talk about all of these things and show them to be utterly wrong.
That's 15.8 light years away. Any star 10 times the brightness of the sun or less would not be visible if it
makes a bunch of assertions here that are not relevant to the immediate point. I would like to go to the examples that he gives. He now talks about magnitude, which of course is fine. Just a little word from about magnitude from me. Magnitude is a very, very annoying logarithmic unit that is brighter when the number gets lower. So for example, the faintest things that we can see in the sky with fancy pan telescopes are usually at the magnitude of around 24 and a half maybe. So yeah, the Sun, Sirius and Vega are all of course in the region where stars typically reside, and note that this is the absolute magnitude and not the relative magnitude. There is a difference there as well. The absolute magnitude is normalized to be at a distance of 10 light years, I believe it was, and the relative magnitude is how we actually see them. So the absolute magnitude is how just bright the star is, corrected for its distance to us, and the relative magnitude is how bright it seems to us.
brighter the star. Sirius at a distance of 8.6 light years is the brightest star in our night sky. Its absolute magnitude is plus 1.43, which means it's about 25 times brighter than our sun.
Thereabouts.
Vega, the fifth brightest star. It's a blue-white star, located approximately 25 light-years from Earth, with its absolute magnitude of 0.58 making it about 50 times brighter than the sun. Vega and Sirius would not be visible.
Note the numbers down here. With your own citations, all of these would be less than a single photon, which would of course be impossible. We know that this is completely working. I've made a similar point in a previous video, but I will also calculate this for us all after he's finished with his statement.
At 1,000 times and 100 times the sun, still would not be visible. HD 140283, also known as Methuselah's star, located about 190 light-years away. At an absolute magnitude of plus 3.377, is only 4 times brighter than the sun. Yet using low-powered binoculars, you can see its light. That's not possible.
It is, and I will briefly calculate it together with the whole thing about the planets. So I would like to start with planets. The basic problem and the way that I approach this. So we have the sun emits light towards the planet reflects some of this light and hits back to Earth. Now in all of these cases, I assumed that the sun and the distance from the sun to the planet would be the same as the distance from Earth to the planet to make things easier, even though this is a special geometric case and it's technically not the average. It saves me from calculating with two different distances here. So essentially the power of the sun is 3.8 times 10 to the 26 watts, which corresponds roughly, we calculated the photon energy to be roughly 4 times 10 to the negative 19 joules in the previous video. That roughly corresponds to 10 to the 45 photons at 550 nanometers every second. So for Mars, if we would like to find out how many photons are hitting the planet, well, we take the amount of photons that are emitted every second by the sun, we divide them by 4 pi times the radius, not the radius of Mars, the distance to Mars squared, because the sun and any light source, roughly point light source that emits its light in the same way in all directions, so without having any preferred direction of emission, has spreads it out over a sphere. I explained this in the first video. So this is what I call the photons at Mars, PM, in yellow here. So the number of reflected photons from Mars, RM, is the amount of photons that reach Mars times the surface of the Mars that is being hit, which is from the sun, you see a half circle, a semicircle. So you see pi r squared. Now this here is the actual radius of Mars times some albedo, which in case of Mars is about 25%, so 0.25 here for albedo. Now we take the photons per square meter because we would like to know these at Earth. So we have the photons at Earth, and the unit is in photons per square meter. We take the reflected amount from Mars and we divide it by 2 pi r squared. Now you might wonder why 2 pi r squared when I above just had 4 pi r squared. I figured even though that's a small detail and it's easy to miss and it just changes it by a factor of 2, Kryptonite Physics technically didn't do it, but I don't blame him for that. I think it's only 2 pi because only half of Mars can reflect, because only half of Mars is in sunlight. The other half is not of any interest to us. So I would argue that the light that is reflected from Mars doesn't spread out over a sphere. It spreads out over a or a hemisphere, or a half sphere, if you will. Yeah, so the amount of photons at Earth in photons per meter squared, we take this as called PE, and now how much can we see of that? Well, we take the amount of photons per meter squared and we multiply it with the radius of our pupil squared times pi, so that we know how many photons would reach our pupil. And for Mars, it's a staggering, at the actual distance of Mars, of course, for Mars it's around 1 million photons, even more than that, which is around 1 times 10 to the negative 5 lux. So it is certainly visible. As we know, that many photons per second are 100% visible. Now I wrote a little Python script that goes through all of these calculations with all of the planets, and these are the results. And well, not all of the planets, all the planets that are further away from the sun than Earth is, and the moon, because he includes the moon. So just as a reference here, those are the photons per second in the eye. This is not in square meters. This is the amount of photons per each second that hit the eye, not only the eye, but at the actual pupil. And here's my verdict whether or not they're visible. Please note that this is only photons per second in the eye. I don't include atmospheric effects. I don't include magnitude, interplanetary extinction, which is a thing, although it's not that strong. I also don't include the quantum efficiency of the light of the rods and cones in the human eye. I think they're about 30%. I could be wrong. So for the moon, we could certainly see it. We have a lot of photons, 10 to the 16 photons every second. For Mars, we have about 1 million. For Jupiter, it's actually more. Jupiter is one of the more brightest things that we can see in the night sky. Unsurprisingly, because it gives us roughly 12 million photons every second. Saturn is about half of Mars, roughly. Uranus is very dim with roughly 8,000 photons. Now this might seem a lot, but you please remember that we don't see light over a second. We see light over roughly a 24th of a second. And if you divide this 8,200 by 24, you reach a rather small number. Now then put together atmospheric effects, extinction, and the only 30% efficiency of the human eye, and you can only barely see Uranus. It also depends on contrast and how much scattered light is around, and if there's a full moon, I suppose, and whether you are in a city or not. And with Neptune, we only get roughly 1,000 photons per second in the eye, which together with all of the effects that I mentioned, we could not see. No atmospheric effects and no efficiency losses. So the distances work rather fine because this is precisely what we see. Now, let's make the same thing with the stars. With the stars, it's actually easier. You just need to know the power of the star in watts, which he has nicely given to us. I went with all his numbers. I did not check because I would like to decidedly check his claim. So it's a lot easier. The photons that reach the eye, again, that reach the pupil, is just the power of the star divided by the energy of the photons. Well, technically, I should say the energy of the star in 1 second rather than the power, because otherwise the units wouldn't fit. So I should say the energy of the star in 1 second divided by the energy of a photon, just as we did above. Then we use the inverse square law here, again, where it spreads over the surface of a sphere. We say 4 pi r squared, with the r being the distance to the star. I picked here the distance to the sun. It's not important. It won't change by more than a few percent. Times again here pi times the radius of the pupil. I said here I because I didn't want to write pupil out. So this is for the pupil, this is the photons per second, and this is the inverse scalar for a star. And now I put all of these things here. So Vega, we can see Vega actually, if you compare it, is just about as bright as Mars, which is very nice. Sirius is very bright, coincidentally just as bright as Jupiter. So this is nice. Both of them, of course, should clearly be visible. And this HD 14 something star gives us about 4,000 photons per second in the eye. So again, I gave here the same verdict as I did here, barely, but even more barely. Apparently, you can only see it with low power binoculars and not with the eye. So the barely here should really be a soft no, but it's right on the edge apparently. Yeah, so it works very well with our model. And now, Chris, I would like to make this abundantly clear here. All of your calculations are based on the assumptions that I mentioned it in the first part, that you cannot see more than 0.0001 lux. This is completely wrong. I have shown here why, and in the description of the last video, and maybe in the description of this video, I'm not sure how I will be doing that, there will be citations that you yourself have given that you can see a couple of photons. So like the one paper gives 5 to 7, but this is under perfect conditions, which I'm not comfortable with. I'll give you a couple that speak at around 100 per some time frame that is reasonable to see for the human eye, right? So, not only have we calculated how many photons would actually reach us, I will now go on and use his very own numbers. As you can see here, he predicts that at the closest mass would give would reflect back to Earth about 0.000056 lux if it's closest, and if it's further away, it's 0.000002 lux. So if you recall, our calculation was about 0.00001 lux, so right in the middle, which is absolutely where I would expect it to be. So we agree in the rough magnitude, in the rough order of magnitude in the terms of the numbers of lux. And I have shown previously when you calculated 2 photons, and actually Chris has agreed with my calculations in the comments on the first video. I will show it here, hopefully, if future Olaf remembers. So not only do we roughly agree on the numbers, he agrees with my math and with how many photons would reach us, and his very own citations, the 2 that weren't made up, or the 3 or something, they give a lot less than that number to be able to see. So Chris is wrong, even by his own admission. He just disagrees because, oh no, in his comments, I don't know, I highly encourage you to read the comments on video 1. It is extremely funny, where he just asserts, no, you need 0.0001 lux to see it, full stop, period, that's it. And I'm like, yeah, whatever, either way. I thank you very much for watching this video. I hope you enjoyed it. If you did enjoy it, maybe consider leaving a like, and if you enjoyed it a lot, I would highly appreciate if you subscribe. And other than that, I will see you in part 3. Looking forward to it, Chris.